Okay, I put in an about me slide. I'm from Minnesota. I've been here for a year and a half, and I'm a traditional sort of DevOps guy. And when that came out, I really identified with it. I don't really know what it means anymore, but I think I identify with most of the things that it means. So regardless of what you actually think it means, I think it's true. Python, Golang, and Red Hats and dark beer, and that's the Minneapolis skyline down there. Okay, so I'm talking about LKFT today. This is like kind of an overview of what we're doing with LKFT and what we've done, especially in the past 6 months. So we're going to go over like the branches we're testing, our architecture, and I'm going to spend a lot of time on the triage process and the reporting process because we've been writing a lot of tooling for that recently, and touch on kernel CI at the end here. So to start with, just for the definitions, it stands for Linux kernel functional testing. And what we test is the Linux kernel. So we don't explicitly try to test boards. We don't explicitly try to test builds and booting. And we don't explicitly try to do performance testing. We're trying to determine if the Linux kernel has any regressions. And we're using boards and builds and boots and things like that to do it. But we're not going out of our way to test a huge variety. We're really trying to go deep into the kernel and not deep into platforms. And we focus on detecting regressions, and especially on the stable tree. So a lot of the things we've optimized for are things that stable needs, not necessarily things that mainline and next need. And here's the caveat, is that LKFT is a framework that a lot of people use, and what I'm going to talk about is how we use it on the kernel validation team to validate the upstream Linux kernel. So some of what I say doesn't apply to like Android teams and things like that. So that's my caveat, and so specifically, we use Open Embedded, for example, but other teams use other things on top of some of these tools. So the branches we focused on are next mainline, and then the stable branches going back to 4.4. And Daniel, following me, is going to talk about how you can test an arbitrary kernel tree based on one of those branches using LKFT. So that's the list we have right now. And this is a representation of our architecture. This is not a technical diagram. So logically what happens is when a kernel branch is updated, we build an open embedded build on that branch for 4 different architectures. And it's actually more than 4 builds because sometimes we have to build separately for each board, which is something that we'd like to improve. We have 4 architectures, like I said, ARM32, ARM64, and then Intel or x86-64 and x86-32, which we recently added. Once the build's complete, Lava runs about 200 jobs, over 200 jobs per environment, and then the reports get aggregated in QA reports, which is Squad. And so Squad is the software, QA reports is our instance of it, and I use them somewhat interchangeably depending on if I'm talking about the software or the website. So don't get confused, they're the same thing. And then we have a triage and a reporting process that we use in order to actually determine if there's any actual problems that we're detecting. So here's the primary boards we use. For a primary board, we look for something that's reliable and that we can scale up, and something especially that has support going back to 4.4. So we test all the way back to 4.4, and we need to be testing 4.4 through year 2022, I believe. And so these are our primary boards. We have the High-Key and Juno, which we use for ARM64, BeagleBone for ARM32, and then we also have x86, and we have all those environments also under QEMU. And then we have this concept of a community board. This is somewhat new for us. And the idea with the community board is that unlike the primary boards, which most developers aren't likely to have on their desktop, a lot of these are expensive or hard to get or impossible to get. The community boards are inexpensive and widely available, and so it's nice to be able to report issues that are reproducible on a board that a kernel engineer might have or might have access to. And so we are running all of our workloads on DragonBoard, and BeagleBone Black is one that we're not yet running, but that's the one that we've identified to be a community board for ARM32. Here are the current amount of boards that we have in our Lava instance. So you can see that we have between 8 to 15 boards, depending on which one. You kind of have to add up the rows here. This is a snapshot I took. I put the URL on the bottom there. just to give you an idea of the scale. The QEMU, we have 2 physical hosts and 14 logical hosts, so 14 QEMU workers. This is an example of what it looks like when we get, this is the Q depth in lava. Each line represents a particular board. And what you're looking at is, I think this is over a 24 or 48-hour period, and this is what happens when there's a stable release candidate. You see after the builds, the lava jobs come in and the Q depth increases, and then you can see the Q getting worked down. And we've been starting to use better analytics to be able to visualize what we're doing in LKFT and to determine where we need to add capacity and things like that. So this has been really helpful, and this is kind of a recent thing that we've added.
What's the scale?
The scale on the y-axis, this is 200, 220, 240, and this is 48-hour period. So this is a typical, when there's a stable release candidate, often there's 4 Git branches that get updated, so this represents 4 builds that happen, or 4 sets of builds, and then all the lava jobs for each of the boards. So, this is 200, I don't know what the blue line is, x86 jobs. So, x86 gets a lot because it's doing, because we only have 4 of them and because it does 32 and 64-bit. Okay, so here's the test we're running right now. We have 10 environments, and for each environment we run k-self-test LTP and libhuge TLBFS. When you multiply those out, it's over 20,000 tests at this point per kernel release that's under test. And so we're actually starting to get to the point where there's a lot of, well, we've always had a lot of test data, but now we really are getting a lot inundated with test data. And so sometimes we have a problem where we're looking at the test and we see a failure, and then we see another failure, and then we see another failure, and pretty soon we don't know what failure to look at. So how do you deal with all the test data that's coming? This is the only GIF in my presentation, by the way. It's tempting to fill. So how do you deal with all the data you have coming in? So I'm going to tell you a story about how we've done it. Originally what happened is we set up all of our lava jobs to do all the testing. But invariably what happens is the tests wouldn't finish, the jobs would time out and things like that, because there are some tests that just cause the boards to hang because they weren't written for embedded devices. A lot of times the tests are written on a developer's desktop or laptop, and so they don't function in our environment. So the first thing we had to do was get the test results in a consistent and reliable way. So we implemented skip lists. So for our skip list, we initially just tried to skip the stuff that caused the test runs to fail. But as a result of that, we still have a lot of failures to go through the data for. So when you're looking at test results and you have, say, 7,000 passes and 350 failures, it's really hard to know when somebody asks you, does this branch look good? Does this release look good? And you're looking at 350 failures, and that's the Dilbert strip, right? It's like, well, yeah, sure, it looks good. I mean, how do you know, right? So the next step, what we did is we started using the regressions and now fixes in QA report. So what you would do is you would compare the previous build to the current build, or the current results, and anything that went from passing to failing was a regression. Anything that went from failing to passing is a fix. And the only problem with that is that there's a lot of tests that we have that sometimes fail. And so those start to make your data look really noisy. So what did we do? So we just started skipping all the failing tests so that we could get down to the signal in the data and figure out what is actually going on in our data set. The problem with that, though, is you can't tell when something gets fixed because you're skipping the tests. And so then we get the question, is this fixed in this release? And we go, well, we don't know. We skipped that like 3 months ago because it was failing. So the result of this is that we were hiding too much data. And so this brings us to where we are today, which is known issues in QA reports squad. So we have the ability now to annotate the failures in the user interface so that it shows you when there's a failure, if it's a known failure or if it's a new failure. And it also, I mean, this is incredibly important, lets us mark something as an inconsistent failure. And so that just means like ignore it completely, as far as I'm concerned, because we don't trust the test. The the problems we have with this is it's still high touch. We still have to go in and like add the known failures and stuff. So the next steps will be further automation on top of this process in order to make it easier for us to maintain all that data that we're maintaining in order to see the signal in the noise. Okay, that's the end of the story. I'm going to talk about how we deal with bugs right now. All of our bugs are public. That's at bugs.linaro.org in a Bugzilla. Oops. In a Bugzilla instance. And the way we classify our bugs, we have a couple different dimensions. Yes, Carlos.
How do you classify intermittent?
We determine that, a human determines if it, the question was, how do you know if it's intermittent? It's not an automated thing, it's a manual thing. And what we do is we look at the history, and we look at it across the branches and across the boards and across time. And it's really obvious when you do that because you'll see the little red spots like Christmas lights in there. And it's usually also a timing test. It's usually pretty obvious because it'll be like QEMU timer something. And you're like, okay, well, this is an intermittent failure. And if we're not sure, we'll investigate it a little deeper. And then we'll add a known issue that's intermittent for that. And then from there on, and this is new for us, the known issues. But the idea is from there on, we don't have to, it won't be causing false regressions to be reported. Did you have something to add, Naresh?
Yeah, just for our knowledge, we are creating a tag as the intermittent in the Bugzilla. So that's where we'll get to know what is intermittent or not.
Yep. And so as a part of our triage process, we open bugs in Bugzilla. Most of our known issues and skips have a bug in Bugzilla associated with it. And the way we classify the bugs is for one using status. And the way statuses are how we implement like a workflow on top of Bugzilla. And so a new bug comes in as unconfirmed, and then we have a weekly meeting where we go through the unconfirmed bugs and do like a shallow triage on them to determine if it's a problem in LTP, for example, or if it's potentially an actual kernel issue, or if it's a build issue. And so we do an initial triage, and that's where it gets assigned to somebody to look at deeper. And that's when we move it to confirmed. Once an engineer starts actually working a bug, then we move it to in progress. Once a patch is proposed or a fix is discovered or found, then we'll move it to resolved. We used to leave them open until the patch was actually applied and backported and all that kind of stuff. But we had so many bugs open that we couldn't do anything about because we'd send a patch, it might even get acked, but you have to wait a certain amount of time for that to be available in the branches that you need it in order for the automation to reflect that fix. For example, in LTP, we have a lot of fixes in LTP, and LTP is released every 4 or 5 months, and so you have to wait 4 months to close the bug if you're waiting for it to show up. And so what we started doing is moving them to moving them to resolved once the fix is known. And then they go from resolved to verified once that fix is available to our automation. So once it actually goes green on our dashboard, then we close the bug. So now we have this set of resolved bugs, and I think I have let me skip and go back. So this is a Bugzilla graph. This is the one graph it gives you over time. The red line is unconfirmed bugs, so the red line represents new bugs that are coming in. And this is the time period is going back to May here. So, and if you can't read this is 10, 20, 30 bugs. So they come in as the red line, and then they move from the red line to the green line, which is confirmed. They move from confirmed to in progress, which is the blue line. So you kind of have to add these lines up in your head to see like our rate over time. Hey, Carlos?
So when you open when a test case fails and a new bug is submitted to Bugzilla, the name of the bug is the name of the test case, or how do you map?
It's not one-to-one. Sometimes we group them together if it's a group that fails in the same way at the same time. We'll group them together, but so that we don't just have duplicate bugs in there.
So how do you map test cases to bugs or test failures to bugs? So when you do the analysis next day and you see a failure, you can check in Bugzilla, oh, I already have, is that in Bugzilla itself?
The test name always ends up in the bug. It's a manual process to open the bugs, so it's not, the data isn't So you're relying on the person that opens the bug to put the data in there, but we use a standard format for the title so that the name is always in the title. And we link back to it from the known issue or from the skip. So if you're looking at a known issue or something that we're skipping, you can see the bug. And we are able to do analytics on top of that to see, like, is this known issue a closed bug? And if so, then why is it still a known issue? And things like that, to do like an audit report. So I'm going to go back. So component we use to classify where the root cause of the bug is. And so we have 4 components. We have kernel. These are the most critical for us when we actually find a kernel bug. These stay kind of at the top of our priority list because these are real issues. General, these would be like build issues in OpenBet that we can fix, things like that. Maybe like a missing kernel config would be a general issue that we hit a lot. And then we find a lot of issues in K-self-test and LTP, like in the tests themselves. Maybe they're making an assumption that isn't true in one of our environments, things like that. And so those are where the bulk of our bugs end up. I already talked about that. So this is our stable triage process. We're committed to responding to the stable release candidates within 48 hours, which for a development organization can be kind of tough because we don't really have 24/7 support or anything like that, and sometimes it's hard to get the data in enough time in order to determine if there's an actual problem or not on a particular release. And so we have a somewhat formalized process for this where we do the build and CI and the triage steps, and then we manually send a reply back upstream once we've looked through the data and made a determination on whether or not there's a regression in the new stable tree. And this is the amount of time that we've met the SLA this year since the beginning of the year. So I guess this is kind of hard to read, but there's been 221 stable release candidates. We've missed our SLA. We've been slower than 48 hours 4 times. And you can see most of the time we're within 24 hours. The one time we missed it, that was one set of, usually they come 4 at a time because there's 4 branches usually. And we missed that one because it came on a Friday night and none of us worked that weekend. So we didn't get to it until Monday morning, which is also our expectation. Sometimes that happens and that's okay for us. Okay, so on to reporting. We have email notifications that come out of Squad. They're automated reports. In our experience, they haven't been very useful for people outside of the triage process because it's hard to know. There's a lot of false failure rates still. We're hoping that the known issues is going to improve that, but in the meantime, I'm just looking at my notes here, yeah. So garbage in, garbage out. A lot of times bad tests create bad reports, and you only get a couple chances to get it right, and then people just start filtering you and ignoring you. And so the automated reports haven't been as useful. We really rely on a triage layer where we look at the results and then we determine if there's something that needs to be reported upstream. With regard to stable, we do respond to every stable RC, and we generate the email using the Squad API actually. And so what we've started doing is using the API to build tools on top of Squad for very custom things that aren't appropriate in Squad, or in a way that we can do much faster in Squad, outside of Squad than inside of Squad. We don't have to wait for a Squad release. We can just use the API to generate the data we need. And so this is an example of that. The email reports that we've been sending to the stable list have been generated using the Squad API recently instead of getting them out of Squad itself. That lets us do things like compare it to a custom baseline. We can compare it to any other version, any other test result we want. So, for example, Squad will just compare it to the previous build because Squad doesn't know anything about our builds. It doesn't know that we're testing the Linux kernel. It's just a reporting interface. But I know that I want to compare it to the last release. And so we wrote a tool that does that. It'll change the baseline so that it uses the previous release instead of the previous patch level, because sometimes we get multiple RCs and the previous patch level might be 0 or 1 or 2 patches different from what's actually released. And so it's not very useful to compare it if there's only one patch. You really want to compare it to the last release.
Quick question about the known issues. You might have mentioned that, and I didn't capture that. So when is it decided that for a known issue, it's time to test it again and take a look if it's been fixed or not? Or are they frozen?
What I anticipate doing is writing a tool that will look at all your known issues and look at all of your results, and if you have a known issue that's passing everywhere, that's not a known issue, and it would flag that and
It
deliver a report
It
that
will show up as a fix in an email report.
forever.
No, just that one time that it flips.
Yeah.
So-
Yeah, it
It's
still
not
may be a
because
known issue
for-
on some environments, though.
Yeah,
so,
for known issue, we run the test still, but ignore the result.
yeah. Okay, so here's a screenshot of QA reports, and some of the recent features that Antonio was talking about that we're using are, this little gear icon is really nice. All three of these icons are new. So the gear icon shows you if tests are still in progress, and it used to be that was kind of hard to determine if a squad calls these builds, but if a version of Linux under test is still being tested, it was hard to know just from this interface. So that gives us that. The red triangle gives us regressions, and the green checkmark gives us fixes. So that's a really nice way, and especially once we get the known issues fully populated in here, it should start to become really easy for somebody who's not familiar with the project to come in and look at the dashboard and understand if there's an actual problem or not. In the past, it's been really hard because if you just come in here, and this was the dog with the tennis ball thing, right? You just come in here and you see 134 failures and you're a kernel engineer, you go, well, I don't know. I mean, is that good or bad? It doesn't have a lot of meaning. And these X fails, this blue box, that's where the known issues are showing up. So we see these X fails, and so previously this would have had 17 more failures and it wouldn't have shown this, but now it's moving, as we add known issues, it's moving them out of failures and into known issues. So. What's next? This is this is a very useful feature that was recently implemented that lets you compare for a given test suite and a given test or set of tests. I always use it with one test suite and one test, but it allows multiple. And then for projects, I will put in all of the branches that we have under test. So I'll put 6 branches in this column. I just didn't have room in the screenshot. And you'll get a table of the test results across, you'll get, I think it's the 10 most recent builds for each branch you select across all of our environments. And it makes, this is, Carlos, where you can see when something is intermittent, because you're looking, if you just scroll down, you're seeing, I don't know how many hundreds of boxes. And if you see red ones, like pockmarks all over the place, you have a pretty good idea that it's intermittent failure. In this case, it's very clear that we have a ARM32 issue, I guess, because I can see the QEMU ARM column and the X15 ARM column are all red. Everything else is passing. Okay, so we also have a website, lkft.linaro.org. This has been kind of it's not very pretty because I made it and I'm not very good at web design, but the homepage, we kind of have our build status here. We kind of have some test results here. Those link into QA reports. And we have some documentation about how we make decisions in the project, and we also have a change log and stuff like that so you can see over time what's happening. What else? Kernel CI. So when LKFT started, Kernel CI was very good at doing build and boots, and that's why on the first slide I said that we don't do builds and boots because Kernel CI does it really well. So we do find build problems and we do find boot problems and we report those, but we don't have tooling around it. We don't try to look for them. We just incidentally find them sometimes. Recently, Kernel CI started implementing functional testing. We're looking to help Kernel CI implement functional testing and bring what we've done in LKFT to Kernel CI. And I put some Kernel CI links here. So I guess that's all I have to say about that. So quick 6-month recap. I don't have a time here, so I don't really know how I'm doing. So Squad has had huge development in the last 6 months. This is kind of since the last Connect. Branches, we're always adding and removing branches as we follow kernel.org for this stuff. So if there's a stable branch on kernel.org that's newer than 4.4 because we don't do the older ones than that, we add it, and as they're removed from kernel.org and removed from support, we remove them from LKFT. We added QEMU ARM64 and ARM32. We added quite a few tests in LTP. We added the CVE tests. We upgraded LTP. We added LTP OpenPOSIX, which added quite a few tests to our environment. K-self-test. So I guess I didn't mention this. We run K-self-test from the latest stable version against the older stable versions. So right now we're running K-self-test 4.18 against 4.4, 4.9, 4.14. On mainline, we run K-self from mainline, and on next, we run K-self-test from next. So it matches on mainline and next, but on stable, we use the latest stable. We upgraded Open Embedded from Morty to Rocco. We implemented fast sanity tests. So this is right now our full regression set takes hours to run. And we had a request to just get like more of a smoke test. And so we implemented a separate, for each branch, we have a separate email report that goes out. And it just does, I think, like 100 test cases and in a single Lava job. And so we have that. And we added Intel 32 support. And that's all I have. Any questions? Anders?
Well, I don't know if it's for this talk or not, but any more information about kernel CI and LKFT collaboration? Or?
Yeah, we're already involved in kernel CI in the build and booting. And so we're trying to figure out what we can do, how we can kind of glue them together, because we're really interested in bringing what we have and collaborating and doing it in a more scalable way that lets us scale into multiple labs and have more community contribution. One of the things we haven't done well is get people from the upstream community involved. And so we're really looking to improve how we do that so that our tests are more useful for people and it's not reliant on us to look through everything ourselves. And
there is already a discussion mainly on the mailing list, so there is no real work done yet between myself and Collabra, so between us and Collabra, who are to have some implementation of functional tests around kernel CI and this.
Yeah, I think you're talking about like the user interface with Squad versus.
Yeah, there's this, we had a couple, like for last month, there were a couple of meetings discussing there, and there was some emails on the mailing list. So I guess this will be a bit more intensive in coming weeks.
Thank you.
Okay.